Good morning. Hope everybody had a good long weekend, had some time to relax a little bit and not think about the test too much. But if you haven't already checked your grade or haven't checked your feedback, I did post a message saying all you have to do is just to go into the grade book. You can click on the actual grade there, and that'll let you look at my comments. They're over to the right-hand side in the margins. And if you click on an individual comment, it'll show you where in the document I made that comment. So you can see exactly which number that corresponded to. That'll also tell you how many points were deducted for each problem based off of what you got correct there. So take some time to review that. Let me know if you have any questions about it if you haven't already looked at it. And student hours are a great time to come in and ask me questions about your test. So if you can, that 9 o'clock to 10 o'clock hour, if you have any questions about anything that you lost points on the test, feel free to stop in during those student hours and ask me those questions, okay? Next thing that's coming up right now is the homework for sections 2.1 to 2.3. Right now that says it's due tomorrow night by midnight. We'll see how far we get today, and I might adjust that date accordingly. It'll definitely be due at some point this week, but it might get pushed back a day or two depending on how far we get. Okay, but as we get through these first couple sections today, at least go ahead and get a start on that homework because you know how long some of these problems might take, and that way you're not getting too far behind and trying to get it all done in one day. Okay, I think that's all I have in terms of announcements. So any questions, comments, concerns before we get started this morning? All right, so we are going to start chapter 2 today. This is section 2.1. The chapter 2 material can be found in the course content folder now. So if you click on that, the chapter 2 folder is unlocked, and you should be able to see all the slides for chapter 2 if you want to use those. Okay. All right, so section 2.1 is derivatives and rates of change. So here's where we're actually going to get into the definition of what a derivative is and how it's related to all the stuff we've already looked at back in chapter 1. Okay, so a lot of this stuff is going to look familiar because we've kind of already done it. Now we're just kind of simplifying the process and we're giving it a formal definition. All right, so the derivative here, oops, sorry about that. Let me go back. That was the wrong section. This is where we're starting. Okay. All right, derivatives and rates of change. Here we go. All right, so tangents. Okay, so no, Paulina, there is no test this Friday. The next test won't be until next week sometime probably. And again, that'll depend on how far we get. It might even fall into the following week, but we've at least got a couple weeks until the next test. Okay. Yep. All right. So if you remember back in chapter 1, we talked about what a tangent line was, remember? And what we said was it's a line that touches a curve at exactly 1 point. So what we're going to do now is we're going to look for a formula that we can use to actually find the slope of that tangent line without having to do those tables of values for our limits like we did back in chapter 1, right? Because remember, that was a long process. We kept choosing points closer and closer and closer to the point that we cared about, calculating those slopes over and over and over again, and then guessing what that slope of the tangent line should be. Now we're actually going to say, well, we know to calculate a slope, our formula is just y2 minus y1 over x2 minus x1. So if we look at this formula down here now, and we take f of x, which is the function itself, and we subtract f of a, which is the value of our y value at the point that we care about. So we're looking at this point right here right now, and we put that over x minus a. That's just a y value minus a y value over an x value minus an x value. But now this will calculate the slope for any point that we choose other than the point that we care about, right? And what we're going to end up doing is taking that f of x value and sliding it around our curve to get it closer to the point that we care about. Okay, so this is the formula to calculate a slope. And then we're just going to think about that slope as we approach that f of a value that we're actually trying to find the tangent line through, okay? To do that, we're going to use limits, right? Because if we take the limit now as we approach that a value, then we know we're going to be able to find the exact slope that we care about. So we're using our formula f of x minus f of a over x minus a to find the slope, and then we're taking the limit as x approaches a of that slope formula. Once we do that, that's going to give us the exact slope at our tangent line now. Okay, so that's what we're using to calculate the slope of our tangent line. And again, all we're doing is we're taking these different values here and we're sliding them around until we get to the point that we actually care about, which is this p-value right here. And that's what the limit's doing for us, so that we don't have to choose all those random points. The limit's going to do that for us, and we don't have to do a table of values anymore. So for right now, main thing you need to focus on is this formula right up here. That's how we're going to calculate the slope of a tangent line from now on, so that we don't have to do tables. All right, so we want to find an equation of a tangent line to the parabola y equals x squared, specifically at the point 1, 1. All right, now to find our equation, first thing we need to know is what is the slope, right? So we're going to use that formula that we just saw. So I'll copy it down here. M equals, I'm going to take the limit as x approaches a of f of x minus f of a over x minus a. All right, now if we're looking for the equation of the tangent line at the point 1, 1, what is the a value going to be that we're approaching this time? One, good, right? So the point that's given here, remember this tells us what a and f of a are. Right, so our a value is going to be 1 this time. So this time we're looking for the limit as x approaches 1. All right, what is our f of x going to be? X squared, right? So the function itself is the f of x, that is x squared. So we're going to put x squared minus, what's our f of a? 1, right? Because again, that comes from the point 1, 1. We're looking at the y value for that point now. So that's going to be 1. Right, now in the denominator, we have an x minus, and then our a value we already said is 1. So we're just taking that formula now and we're substituting everything in that we know. The f of x will be the function itself. The a value is whatever the x value is of the point that we're looking for. And then the f of a is the y value that corresponds to that x value. If that whole point wasn't given, if it was just given as 1, then we could plug the 1 in, but 1 squared is 1, and that's how we could get f of a also. All right, now we have a limit that we can actually calculate. So how are we going to calculate this limit? Good, right? We can't direct substitute because we would get 0 in the denominator, so we are going to have to factor this time. We'll take the limit as x approaches 1. What are the factors of the numerator going to give us? Good, it's a difference of squares, so we have x minus 1 times x plus 1, and we have x minus 1 in the denominator. If we simplify, good, the x minus 1 is going to cancel out. We're going to have limit as x approaches 1 of just x plus 1 now. And so what would that limit give us? Good, right? So we can direct substitute there, 1 plus 1. That's going to give us 2. And remember, this is the formula to calculate our slope now. Any questions about that formula or how we used it here? All right, now once we have our slope, we still need to find the equation of the tangent line. So what do we have to do now? Okay, we could solve for b, find the y-intercept, right? So if you want to do slope-intercept form here, y equals mx plus b. In this case, what's our y value going to be? 1. We know our slope we just calculated is 2. What's our x value? Also 1. And then we can solve for b from that, right? So 2 times 1 is 2. Subtracting 2 from both sides here gives us a -1 as our b value. So what's the equation of our tangent line going to be then? Good. So you have y equals 2x minus 1. Now, the other way, if you remember back in chapter 1, we talked about point slope form, right? You could use that also. In this case, that would give you y minus the y value, which is 1, and then the slope times x minus the x value, which is also 1. Again, you can leave it just like that. If you want to get it into slope-intercept form to match the other one, we'd have y minus 1 equals 2x minus 2. And then when we add the 1 to the other side, that also gives us y equals 2x minus 1, right? So either way, you're going to get the same equation, so whichever formula you want to use is fine. Now, if you remember, back in chapter 1, we did this exact problem. We did it before we knew the definition of a limit, though, so we couldn't use limits to calculate it, and we actually had to choose all these different values and create our table and calculate the slope over and over and over again. But we eventually got down to the fact that the slope was approaching 2, and we found that same equation of our line. So we've done this problem before. Now we just have a simpler way to do it now that we understand limits. Any questions on that one now? All right. Now, we have a different formula that we can use, and this is the one I'm going to use from here on out because this one is universal no matter what point we're approaching. Okay, so in this case, we're still approaching a f of a, right? That hasn't changed. But now instead of taking the limit as x approaches a, we can just take the limit as h approaches 0, where h is our denominator. And what we're saying with that is that now instead of going from some x value to some a value, we're saying the difference between those 2 points now is h. Right? So that's basically still just subtracting x minus a, where x is a plus h, the a value is a, but when you cancel out the a values, you just get h. And now we can just look at that limit as we approach 0 every single time. So it's just a simpler way to think about it, so we don't have to have a different formula every time where x is approaching some different value. Now h is always approaching 0, h always goes in the denominator, and now we can just look at f of a plus h minus f of a in the numerator. Now, if you notice, that's our difference quotient that we looked at in the previous chapter, right? So that's where I was saying before, this is going to be a really important formula to be able to simplify, because now we're going to take that difference quotient, we're going to take the limit as h approaches 0, and so we're going to have to know how to simplify this thing to be able to actually direct substitute, since we can't do it with h in the denominator. All right, so now we want to find an equation of the tangent line. This time our hyperbola is y equals 3 over x, and we're looking at the point 3, 1. So again, this time I'm going to use that new formula. We're going to take the limit h approaches 0, f of a plus h minus f of a all over h. All right, so first step, let's substitute what we know in here. Taking our limit as h approaches 0. What's our a value this time? 3, right? So this is still going to give us a and f of a. So now when we substitute, though, we're going to get f of 3 plus h minus f of 3 is just going to be 1 all over h. Okay, so we're not replacing any h's with anything, right? Because that's the value we're approaching 0. So it's just the a values here that get substituted, and then that f of a just becomes 1. Any questions just on that setup here? Okay, now we need to find f of 3 plus h. So what is f of 3 plus h going to look like here? Anybody else not able to see the screen? You can see it. Anybody else having issues? Rachel, it might just be your connection there. You might just want to restart your computer and come back in and see if that helps. Okay. All right, so if we're calculating f of 3 plus h here, what's f of 3 plus h going to look like? Good, right? So it's going to be 3 over 3 plus h because we're just substituting 3 plus h in place of the x right in here in this formula. Okay, then we have our minus 1 all over h. Now, to calculate that limit, obviously we can't direct substitute because we'd get 0 in that denominator, so we have to simplify this first. How could we simplify this so that we could find this limit? Okay, so the first thing I see is we have a compound fraction, right? We've got a fraction in the numerator of a fraction. How could we get rid of that fraction? Okay, so we can't cancel out the 3 because remember, there's addition in the denominator. Those can't be split up. So we can't just go in there and cancel out the 3 because it's not a factor of terms. Okay. Um, so we don't have to actually multiply by the reciprocal here. You could, but if you do that, that's still going to just give us a fraction when we multiply by the 1, right? So what could we multiply by instead that would just completely get rid of that fraction in the numerator? Okay. So you could change the 1 to a 1 over 1. Then you'd need a common denominator to actually combine these. We can't multiply by 0. That's one thing we're not allowed to do, right? So if we multiply by something here, it's going to have to be something that's not 0. Uh, just multiplying by 3 is not going to work either, okay? So tell me this, right? Let's say I had 1 over x. If I want to get rid of the x in the denominator, right, for instance, what would I need to multiply by? This is all over h still. Yeah, if I multiply by x, then that's going to cancel out the x, right? So I can multiply by x up here, but then whatever we do in the numerator, we have to do in the denominator, so I'd have to come down here and do the same thing, okay? Because now the x's would cancel up top. I'd have 1 over xh is what that would look like. Well, if that's the case, then what could I multiply this by to do the same thing, to cancel out that fraction that I've got in my numerator? 3 plus h, right? So multiply by that denominator, 3 plus h, and whatever we do in the numerator, we have to do the same thing in the denominator. So basically, anytime you have a compound fraction like that, if you just multiply by that denominator, it's going to cancel it out, and we just have to remember to multiply top and bottom by the same thing. Any questions about that? All right, now, if we multiply, just remember we have to distribute that 3 plus h to both of our terms. What's that going to give us when we multiply the numerator by 3 plus h? Okay, so it's not going to simplify down that far. And we shouldn't have enough. So let's think about this, right? If I just multiply 3 plus h times that fraction, what's that part going to give us? Just 3, right? Because the 3 plus h cancels out. So we're just left with 3 minus. And now if I distribute this to 1, what's that going to give us? Good, right? We're just subtracting 3 plus h from that now. Right, so if I distribute the 3 plus h, it cancels out the 3 plus h in the denominator of the fraction, leaving us with just the numerator of 3. And then 3 plus h times 1 is just 3 plus h. And we just have to remember we're subtracting that, so keep it grouped together in parentheses there. Now in the denominator, I'm going to keep this factored. So I'm going to keep my h times 3 plus h. Any questions on that step now? And that's going to be a really important strategy as we move forward, because there's going to be a lot of times where we end up with these fractions within a fraction and we have to get rid of them. This is going to be our best bet most of the time, is just to find that denominator, multiply top and bottom by the denominator to get rid of it, so that now we have a fraction we can work with. Okay? Now, if we simplify this numerator now, what's that going to give us? Okay, good. So it's 3 minus h. The 3's, though, are going to cancel out. And so all that's going to be left here is a negative h. And it's still over h times 3 plus h. Okay, so the 3 minus 3 cancels. And then don't forget to distribute that negative to the h. So it is a negative h now. Now, how can we simplify that? Yeah, the h's cancel out. So what's going to be left in the numerator if we cancel out the h's? Negative 1, right? So don't forget it was negative. So it is a negative 1 over, and if the h cancels out in the denominator now, it's just a 3 plus h. Now we can direct substitute to find our limit. So what's our limit going to be at this point? Good, negative 1/3, because we get negative 1 over 3 plus 0, which is just negative 1/3. All right, so take a minute, look over all that work. Okay, are there any questions about any of the steps that we did there? The second step, are we looking right here, Rachel? Yeah, okay. So are you okay with the formula that we've got set up there, just how to go to the next step from there, or are you confused about how we even got that part? I guess, or is it the going from the formula to that step, or going from that step to the next step? Okay, how did I get to the next step? So at that point, I substituted 3 plus h into the function. And remember, the function here is y equals 3 over x. Okay, and so we're just substituting 3 plus h in place of the x now. That's where I got the 3 over 3 plus h. The f of a was 1, so we subtract 1 and that over h. Okay. Does that make sense, Rachel? Good. All right. And so then Albert said, how does negative h turn to negative 1? Cancellation. Exactly, right? So the h's here cancel, right? So I'm canceling out this h and that h, and then I'm left with a negative 1 factor in the numerator and just the 3 plus h in the denominator. Any other questions there? Okay. Now, once we have this slope, we still need to find the equation. Right? So what are we going to have to do now? Okay, good. So either point slope form or use slope intercept, does not matter. So if you use point slope, that's going to be y minus 1 equals negative 1/3 times x minus 3. And we can stop right there, right? So if you want to distribute and get it into slope intercept form, feel free. But I'm fine if you just stop at that point. If you're using slope intercept, just to show you what you would get here, this would give us negative 1/3 x. This would become a plus 1. And then when we add the 1 to both sides, y equals negative 1/3 x plus 2. Okay, so again, either one of these answers right here would be acceptable. Any questions on example 2 now? All right. Velocities. Okay, so suppose an object moves along a straight line. This could be either vertical or horizontal, does not matter. According to an equation of motion, S equals F of t, where S is the displacement, and displacement here just means a directed distance, right? So either left, right, up, down of the object from the origin at time t. So we're basically saying, all right, we're always starting from time t equals 0, that's the origin, and we're traveling in some direction now where positive velocity, let's say we're moving left to right, positive velocities would be to the right, negative velocities would move to the left, and displacement now is just how far have we actually traveled from our starting position of the origin, right? So even though we might travel to the right, and then back to the left, and then back to the right again, it's wherever we end up, how far is that from the starting position? That's what displacement is. And now the function f that describes the motion is called the position function of that object. Okay, so we're going to be looking at position functions, and then how are those related to our velocities now. Now, to find an average velocity, we're basically just calculating the slope between 2 points on our displacement curve, right? So we've got this curve here that represents our position, and we're saying, well, if I know my position here and I know my position here, if I just find the slope between those, that'll give me the average velocity between those 2 times, right? And the way we're going to calculate that is f of a plus h minus f of a all over h, because that's how we find a slope, where again, h now is just the difference between the a plus h value and the a value. And again, key here, this is the average velocity between 2 points of time. Now, sometimes I might want to know, well, what is my exact velocity at a specific moment in time? And we call that instantaneous velocity. The way we're going to find that is by now taking the limit as h approaches 0 so that I get my velocity at a specific moment in time, in this case, whatever that a value happens to be, okay? So our instantaneous velocity is just v of a equals the limit as h approaches 0, f of a plus h minus f of a all over h. Now, you might be saying, well, that looks very familiar. Well, yeah, this is exactly how we find the slope of a tangent line. It's the same thing as our instantaneous velocity now, right? So the slope of that tangent line at that moment in time is the velocity at that point in time also. So nothing new here, except now we have an application for it, where if we know our position function, we can actually calculate the velocity at any moment in time. All right, so now we want to suppose that a ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground. We want to know the velocity of the ball after 5 seconds. Now, again, we've seen this question before, right? We had to create a table of values to do it. Now we're going to see if we can do it using our formulas so that we don't have to do all those different slopes over and over and over again, okay? Now, again, the first thing we need to know is what is the position function that we're going to be using. This is going to be f of t equals 4.9 t squared. And again, that's a formula that would be given to you if I gave you a problem like this on a test, okay? All right, so what I want to do now, I'm going to just try to find a general formula for any moment in time. And the reason I'm going to do that is because I see there's 2 parts to this problem. One where we're looking at 5 seconds, what's the velocity? And then we're also looking for a velocity when it hits the ground, right? So I'm going to have to do this twice. Rather than doing my limit twice, if I can find a generalized formula for my limit, then I can just plug in my values and find both of these velocities using that same formula, okay? So we are starting with our limit as h approaches 0. And we know this is going to be f of a plus h minus f of a all over h. So that's our general formula now for a velocity. Now, instead of plugging in a specific a value, which in this case we could plug in 5, right? And that would we would get our answer for this one and we'd move on. I'm going to just use a general t value to represent my a now, right? So instead of saying f of a plus h, I'm going to say, well, let's let this be the limit as h approaches 0 of f of some time plus h minus f of some time all over h. And you could leave it as a if you want to, right? I'm just using t since f of t was our function up here. And that way we can actually get it just in terms of any random amount of time that we want to use. All right, now let's see if we can simplify this. What would f of t plus h look like based off of our function that we've got this time? Okay. All right, so it's 4.9 times t plus h squared. Good, right? So we have 4.9. We're substituting t plus h in place of t, so that's t plus h, and then all of that gets squared there. Okay, then we're going to subtract f of t, which is just the f of t function now. So this is just 4.9 times t squared, all over h. So again, this now should give us a velocity function for all points of time t, and then once we have that function, then we can just plug in whatever t values we want to find those instantaneous velocities. Well, now we just need to simplify that numerator so we can actually calculate this limit. So what would I have to do first to simplify the numerator now? Good, expand up top, right? So if we square the t plus h, okay, and I'm just going to go ahead and do that because I know we've done that enough times. Hopefully we know what that is. It's going to give us t squared plus 2th plus h squared. Okay, and then we're still subtracting the 4.9 t squared. And that's still over h. Any questions on that step? All right, so next thing, I'm going to go ahead and distribute this 4.9, so then we can combine like terms up there. So that'll give us 4.9 t squared plus 4.9 times 2 here should give us 9.8 th. And then 4.9 times h squared, 4.9 h squared, and minus the 4.9 t squared, all over h. All right, now, if we combine like terms and simplify the numerator, what's going to be left this time? Good. So just the 9.8 th and then the 4.9 h squared, right? And then that's still over h. So let me keep all of that for now, and then we'll simplify that. So we've got 9.8 th plus 4.9 h squared all over h. Right? And at this point, right, we do have that common factor of h that we can factor out. So I'll go ahead and do that. So that'll leave us with let me factor out the h up here first. H times 9.8 t plus 4.9 h all over h, which means we're really just taking the limit as it approaches 0 of 9.8 t plus 4.9 h. Any questions about how we got to that point? Okay, now if I take the limit as h approaches 0 here, what's that going to give us? Yeah, just 9.8t, right? Because the h is approaching 0. I plug that in. Now we have 9.8t plus 4.9 times 0 as our h value. That term cancels out, and we're left with just 9.8t. So this right here represents our velocity function now. Okay, so regardless of what value of t we have, I can always use this to calculate the velocity of that object. Okay, so now going back to part A, if I want to know the velocity of the ball after 5 seconds, what are we going to do? Just plug in 5. Exactly, right? So I'm looking for v of 5, which is just going to be 9.8 times 5. And that should give us 49. And then what do you think our units are going to be in this case? Okay, it is going to be meters per second, because remember our numerator here represented a displacement, right? A difference in our distances. Our denominator was a difference in time. So this is now meters per second as our velocity at 5 seconds. Okay, so this answers part A. Any questions on that? All right, now part B, I'm going to make a new slide so we have room to work this out. We want to know how fast is the ball traveling when it hits the ground. So if I want to know how fast it's traveling when it hits the ground, what are we going to have to find first? So that's eventually what we're trying to get to, right? Is what is its speed, its velocity when it hits the ground. To be able to calculate that, what do we need to know? All right, so good, right? We know the distance from the top of the tower to the ground is 450 meters, right? So what we're going to want to do is set that position function equal to 450 to figure out how long it even takes to get there. So that's our first step. We got to find our time here. To do that, we're going to take our function, which was f of t equals 4.9t squared. And we're going to set that 4.9t squared equal to the total distance to the ground, which is 450 meters. Now we have to solve for t, right? So what's our first step here if we're going to solve this for t? Good. Divide by the 4.9. So if I do that, I have t squared equals, I'm going to round this to 4 decimal places. Okay, so 91.8367. Okay, so this is not going to be exact, right? But I think it's easier just to do it this way than to keep our square root with a fraction in it. Okay, so then we do have to take the square root to get t by itself. And so if we take the square root of that to 4 decimal places, what will we get? Good. 9.5831. Okay, so that's the value of t now. That's how long it would take the object to actually hit the ground to travel those 450 meters. Now, how are we going to find our velocity when it hits the ground then? So if I know how long it takes to hit the ground, good. We already know our velocity, right? Our velocity function. So now we can just substitute this t value into that. We're just going to take v of 9.5831. Remember, our function there was 9.8 times t. So we're just multiplying 9.8 times 9.5831. And so if we do that, what does that give us as our velocity this time? Okay, good. So I'm just going to round that to one decimal place here. So 93.9. And then the units again are going to be what? Meters per second again, right? So our distance was meters, time was in seconds. And so this is how we would find part B now. So again, the whole reason that I found the formula first was because I knew I was going to have to do my velocity 2 different times. So rather than doing that limit twice, I can just find the generalized formula for my velocity. And then once I know my times, I can just plug in multiple times to find the different velocities. Any questions on that part now? All right. Derivatives. Okay, so here's our definition of a derivative. And this is our limit definition. So the derivative of a function f at a number a is denoted by f prime of a is the limit as h approaches 0 of f of a plus h minus f of a all over h. And again, this is depending on whether that limit actually exists, but as long as it does, that's our formula to calculate a limit. Now, the way we read this right here is we say f prime of a. Okay, so that's how we read that f with the little apostrophe next to it is f prime. Now, again, you might be saying, well, wait a minute, that looks similar to everything we've been looking at. And it is. So whenever you're finding a derivative of a function, you're really just finding the slope of the tangent line at a given point. Okay, that's all a derivative really is now. So we're still going to use that same limit definition that we used to find the slope of a tangent line. That's going to give us our derivative now. And again, you can see the formula at the bottom. That's the first one we looked at. Again, I'm going to use that limit as h approaches 0 formula, but either one of these will give you the same thing, right? So it doesn't really matter which one you use. All right, so we want to find the derivative of the function f of x equals x squared minus 8x plus 9 at some number a, right? So we're finding a generalized derivative now for any number a that's part of that function. So again, our formula from the last slide, f prime of a, that's our derivative, is the limit as h approaches 0, f of a plus h minus f of a all over h. So just make sure you commit that formula to memory, right? Because you're going to have to know how to do this limit definition of a derivative. All right, so now if we calculate this limit, let's start with the f of a plus h. Okay, so how are we going to get f of a plus h? Okay. So be careful here, right? So we're finding a generalized formula, right? We don't have a specific value of a or anything like that. So what are we going to have to do to find f of a plus h? Yeah, substitute the a plus h into the function, right? So everywhere I see an x, I'm going to substitute a plus h instead. So when I do that, that's going to give us a plus h squared minus 8 times a plus h plus 9. This is very similar to that first problem on our test. The only difference is we weren't calculating a limit yet. We were just finding the difference quotient, the f of a plus h minus f of a over h, right? Now we need to subtract f of a. Well, f of a then should just be the same function, just with a substituted instead of x, right? So that's going to be a squared minus 8a plus 9 all over h. Any questions on that step? Okay. Now that we have our difference quotient, now we need to simplify it so we can actually calculate this limit. So we are going to have to expand. So remember, a plus h squared, again, that's one we've done a lot. So that's going to be a squared plus 2ah plus h squared. Now I can distribute that negative 8. So this can give us a minus 8a minus 8h. We have our plus 9. And then we have to distribute the negative since we're subtracting that entire function. So minus a squared plus 8a minus 9. All over h. Now, if we simplify the numerator and combine like terms, what's going to be left now? Good, right? So we have two AH plus h squared minus 8h all over h. Because in this case, we have an a squared minus a squared. Those are going to cancel. We have a negative 8a and a positive 8a. Those are going to cancel. 9 minus 9 cancels. So we're only left with those other three terms now. All right, what can we do at that point? Factor out your h. Good. So if we factor out the h here, we'll have 2a plus h minus 8 all over h. And again, we've done this a lot. Those h's now should cancel out. And now we should be able to find that limit So what's our limit going to be as h approaches 0 now? Good. So we just have 2a plus 0 minus 8, which is just 2a minus 8. So that is our derivative now. And again, this is useful because now if I want to know the slope of a tangent line at any point on that curve, all I have to do is plug in whatever a value I'm given into this 2a minus 8, and that'll tell me exactly what the slope is no matter what point I want to find it at. Okay? Absolutely, Dean. Yeah, it's coming. 2.3 is where we do the shortcuts. Okay, so we have to start with the limit definition first, and then 2.3 we'll get into the shortcuts. Any other questions here? All right, so derivatives. The tangent line to y equals f of x at a f of a, right, that point that we've been looking at, is the line through a f of a whose slope is equal to f prime of a, which is the derivative of f of a at a. I've already mentioned this, right? But again, this is a key concept that you need to make sure you keep in your mind. Anytime you're calculating a derivative, all you're doing is finding the slope of a tangent line at a given point. So f prime of a, that derivative is just the derivative, the slope of the tangent line at that specific point A. If you find the generalized formula, that's the slope of all the tangent to that function, no matter what A value we want to choose. Okay? So just keep in mind, calculate a derivative, you're finding slope of a tangent line. That's what you need to know. All right, so now we want to find an equation of the tangent line to the parabola x squared minus 8x plus 9 at the point 3, negative 6. Okay, now that's the function we just looked at, right? So we don't have to redo the whole calculation if we don't want to because we already know it. So what do we know our formula is going to be to calculate this time? So if this is the same function we just looked at in example 4, and I need to know the slope. Exactly, right? So 2a minus 8 was our derivative, and we already said the derivative is just the slope of a tangent line. So we can say, well, m is just f prime of a, which we calculated on the last example and got 2a minus 8. Well, what's our a value now? 3, right? So this time we're given a and f of a. So now we can say, well, m equals f prime of 3, which is just 2 times 3 minus 8. And so what's our slope going to be this time? Negative 2. So again, once we have that generalized formula for our derivative, now we can calculate the slope at any point we want to. They give us the point 3, negative 6. We just plug in 3 as our a value. That gives us our slope. Now that we have that, we still need the equation, right? So how are we going to find the equation of our tangent line? Point slope, okay? We'll do y minus negative 6 equals -2 times x minus 3. This becomes y plus 6. You want to distribute here and get it in slope-intercept form. That would give us -2x plus 6 over here. Subtracting the 6 cancels out, and you're left with y equals -2x. That is the equation of our tangent line through the point 3, -6 now. Any questions there? And obviously, if this, they didn't give you the example before, you'd have to do that work, right, to get your formula. But then once you have that formula, just plug in the 3 for your A. That gives us our slope. Then you have your point and your slope, and then you can find the equation of the line. Now, one nice thing about these is you can actually check yourself by looking at it graphically, right? Because we know what we should have found here is the equation of a tangent line to that specific curve. I'm going to switch over to Desmos real quick and just show you how you can look at this just to make sure that your answer makes sense. All right, so the function here was y equals x squared minus 8x plus 9. There's our curve, looks like that. We're trying to find the tangent line that goes through 3, -6, right? So that's this point right here on our curve. And the equation that we got is y equals -2x. And there you go, right? So y equals -2x is indeed a line that only touches that one point on our curve now. Okay? All right, so let's take our break here. We'll take 5 minutes, so 11:07. We'll come back and we'll get started on section 2.2. All right. So, like I said, this is section 2.2 now, the derivative as a function. So what we're going to look at now is exactly the same formula we just looked at, but now we're going to interpret this as an actual function of another function. Okay, so instead of just saying f prime of a, where a is some random point on the curve, now we can actually find f prime of x, where it represents a new function that is now the slopes of all the tangent lines to the previous function that we started with. So again, formula looks very similar. The only difference now is instead of an a, we have an x. So this becomes an x right here, and this becomes an x right here, but the calculations are still the same. Okay, so we're just using x instead of a so that it now represents a function instead. Right, now, the first thing we want to do, let's see if we can think about what the graph of the derivative function would look like if this is the original function. Okay, so we're going to actually try to interpret visually what this would look like, and then we'll do some algebraic calculations down the road to actually find some functions. All right, so if f is given here, we want to sketch the graph of f prime. Remember, f prime just represents the slopes of the tangent lines at given points on that curve. Are there any points on this curve right now where you could say, yeah, I pretty much know the slope of my tangent line would be whatever? So are there any points where that might be easy to find? This way. Okay, so all right, so it looks like 0.51. All right, so you're saying this point right in here. What does it look like the slope of the tangent line would be at that point? 0, right? Because at that point, if I were to put a tangent line here, it looks like that tangent line would have to be horizontal, right? And a horizontal line has a slope of 0. So when I sketch that point, I'm going to come down here and do another graph and try to line all this up. So if this is 1, halfway in between there, if this represents our derivative, f prime, we know we should have a derivative of 0 at that point, because there we would have a horizontal tangent line. Where else might we have tangent lines like that? Okay, so yeah, so somewhere between 1 and 2, up here at this point right here, looks like we have another horizontal tangent line. So again, our slope would be 0 there. And then we have this other point right down here, where it looks like we would also have a horizontal tangent line. That slope would also be 0. So when I draw these points on here now, again, I'm trying to line them up. So I know I'm going to have 0 for my derivative here. And if this is 2, this is 3, I'm going to hit 0 right here also. So that's how I typically start, right? As I say, all right, where do I have those turning points where my horizontal, where I would have horizontal tangent lines, and I know my slopes would be 0. That's where my derivative then should cross the x-axis because it's going to have a value of 0 at those points. Any questions there? All right, now at that point, I'm going to say, well, let's just figure out where our slopes are going to be positive and negative. So at least I have a general idea of where this curve is going to go, right? So if we start over here on the left, would the slopes of my tangent lines over there be negative or positive? starting from the leftmost point, as I move to the right here, are those slopes going to be negative or positive? Negative, right? Because if I put a tangent line, at any point in between there now, okay, all of those points should have a negative slope, right? So I know that my curve is going to have to start down in the negatives. So I'm going to start somewhere down here. Okay, sorry. I'm actually going to erase this line and move it up just so I've got room to work. Okay. All right, so we know we're starting down here in the negatives, and eventually we're going to work our way up to this point, okay, which we said should be 0 there. Now, once we get beyond that point, what happens to the slopes of our tangent lines? So at 0.5, we know the slope is 0. And then between 0.5 and 1.5, what does it look like our slopes would be there? They're going to be positive, right? So all of my tangent lines in here now, it should have a positive slope to them. And so I'm going to say, well, now my graph goes up into the positives, but eventually it has to come back to 0, right? Because I know that my slope at 1.5 is going to be 0. So even though I go up here into the positives, eventually it's going to have to curve back down, and it's going to go back to 0. Now, once we get to 1.5, now what happens to our slopes? They're negative again, right? So everywhere in here now, if I were to draw a tangent line, okay, those are going to have negative slopes everywhere between that 1.5 and 3. My curve's going to come down like this. But again, eventually I'm going to have to come back to 0 once I get to 3. So it's going to curve down. And it's going to come back up again. And then once I get to 3, then what happens to our slopes? They're positive again. If I were to draw a tangent line anywhere on this side, and notice they're approaching infinity, right? Because as I go on, it gets steeper and steeper. So this is just going to curve up like this and just continue on towards infinity now. Now, not a perfect graph, right? We don't know enough information to get exact points along this curve, but we can at least get an idea of what that derivative curve should look like, right? We know where the derivatives are going to be 0 by those turning points. We know where it's going to be positive and negative, so we at least know the basic shape of what this derivative graph should look like now, okay? Any questions on that? All right. Now, if we're given the function f of x equals x cubed minus x, we want to find the derivative function f prime of x this time. And then it says to illustrate by comparing the graphs, we're going to go to Desmos and actually look at our original function, what we got for the derivative, and then look at how those two graphs are related to each other. So first step, though, we've got to find f prime of x. So we're still using that limit definition, okay, and this time again, instead we're going to use x instead of a. That's the only difference. So limit h approaches 0, f of x plus h minus f of x all over h. All right, so we have to start by finding f of x plus h. How do we do that? Good, just plug in x plus h to your function. So this time that's going to be x plus h cubed minus x plus h. All right, then we're subtracting f of x. So we're subtracting the f of x function, which is just x cubed minus x all over h. All right, so if I cube x plus h, what is that going to give us? Good, right? So remember, that's just x plus h times x plus h times x plus h. You could always multiply it out if you need to, but if you know that general formula here, it should give us x cubed plus 3x squared h plus 3x h squared plus h cubed. All right? All right, now we're subtracting x plus h, so distribute the minus. That's going to give us minus x minus h. And then we can distribute this minus to everything in our function. So that's going to be minus x cubed. And that becomes a plus x all over h. All right, now we can combine like terms. So what's going to be left in our numerator once we do that? Good, 3x squared. Let's see, there should be an h on that term, right? Because the x cubes cancel out, and then the x's cancel out. So we have that plus 3xh squared plus h cubed minus the h. Okay, all over h. All right, so then what can we do at that point? Good. Now we can factor out our h because we have an h in common with all of our terms. So h times 3x squared plus 3xh plus h squared. And then this is going to be a minus 1 where that h was down there. Okay. All right, now if we cancel out the h this time, now we can direct substitute. And so what are we going to get for that limit? Okay. All right, so be careful here, right? Everywhere we see an h, there's going to be a 0 now. So this is going to give us 3x squared plus 3x times 0 plus 0 squared minus 1. So now what's that actually going to simplify to? Good, right? The 3x term actually becomes 0, so the only thing left is 3x squared minus 1. That is our derivative function now. Anybody who's had calculus before, right? You can use the shortcut and see the derivative. That is the actual answer here. Any questions on how we got there? Okay, so again, keep in mind, right, the derivative represents the slopes of the tangent lines to the original function. So what I want to do now is I want to look at both of these curves graphed together in Desmos and look at how those slopes of the original function are related to the function that we got as our derivative. All right, so original function here was x cubed minus x. So that's what that looks like. And then our derivative function that we got was 3x squared minus 1. So those are the two curves. I'm going to zoom in a little bit so we can focus just mainly on this inner part here. All right, so where on the original curve, which is the purplish blue one, okay, that's this one, what slopes do we know for sure based off of looking at that graph? So you give me approximate points here if you need to. But where does it look like we would know the slopes for that curve now? So think back to example 1 and the points that we started with. What slope values would be easy to find here for that original curve, the blue one? Okay, all right, so that works, right? So plus or minus something between 0 and 1, right? So 3/5, probably a good estimate. If you look right here, right, it's a weird decimal, okay, but that point and that point right there, right? So just over 1/2 and just less than -1/2. Those are the points where you would have horizontal tangents, right? And we know at those points, the slope should be what then? 0. So our derivative graph then should cross the x-axis at those points because that's where our slope should be 0. And if you look here on the derivative curve, that point matches up and that point matches up, right? So at those points now, the slopes are indeed 0. Now, to the left of those points, are the slopes of the original curve going to be negative or positive? Left-hand side, that's going to be positive, right? All the slopes of those tangent lines on the left for that original curve should be positive until we get to that point. Well, if you look at the black curve now, everything on the left of that parabola is in the positives, right? It's above the x-axis, okay? So those derivatives make sense. Once we get to that point where we have a slope of 0, everything between that point and the other point where the slope is 0, those slopes are going to be what? So from negative 0.57 to positive 0.57, all of those slopes of the original curve are positive or negative. looking at the slopes here of all these points. Good. All of those slopes are going to be negative now in between these values, right? And so if you look at the black graph, which represents the derivative, all of those points now are below the x-axis in between there, so our derivative is negative. And then once we get to that value 0.577, everything to the right of that point on the purplish blue graph, are those slopes going to be positive or negative? Those slopes are going to be positive, and so the black graph should be above the x-axis beyond that point, and it is. All right, so you can see in this case, we have those horizontal tangent lines. That's where the slope is 0. That's where our derivative crosses the x-axis. And then we can think about our positive and negative slopes, and those match up with that parabola that we've got now. Right? Everything where there's a positive slope of our tangent lines should be above the x-axis. Anywhere where the slopes are negative should be below the x-axis. Any questions on that now? All right. All right, so now we're given f of x equals square root of x, and again, we want to find the derivative f prime. This time it asks us for the domain also, so we'll do that once we actually have the formula for the derivative. All right, so same formula we just looked at. So f prime of x is going to be the limit h approaches 0, f of x plus h minus f of x all over h. Again, just write that down as many times as you can because you're going to have to memorize it, and the more you write it, the easier it'll be. All right, so again, we're substituting the x plus h into our function. We're going to have the limit as h approaches 0. This time, if we plug in x plus h, that's just going to give us the square root of x plus h. And then we're subtracting f of x, so minus square root of x, all over h. All right, now, if we want to calculate this limit, what are we going to have to do this time? We can't direct substitute here. So what would we have to do to simplify this first? Okay, so remember, we're not allowed to square, right? Because you can't do that to the numerator and denominator. It gives you different values. So what do we have to do? Have square roots, the conjugate, right? Remember, anytime you have a limit that you can't calculate because you'll get 0 in the denominator, we can multiply by the conjugate here, see if it simplifies, and then maybe we'll be able to direct substitute. So the conjugate for this one, we're going to have square root of x plus h. And instead of a minus, it's going to be a plus square root of x. And whatever we do to the top, have to do the same thing to the bottom. And this goes back to those limits that we looked at in the previous unit, right? Anytime you have square roots, you can't direct substitute, multiply by that conjugate, then simplify. Well, what's the numerator going to give us then if we multiply that out? Good, right? So the square root of x plus h times the square root of x plus h, that gives us x plus h. The outer and inner terms are going to cancel every time, right? Whenever you multiply by the conjugate, and then the square root of x times the square root of x. One's negative, one's positive, so that's just a minus x. Keep the denominator factored, so we're going to have h times the square root of x plus h plus the square root of x. All right, now simplify your numerator. What's that going to give us in the numerator if we do that? Good, right? The x is canceled. You're just left with h over h times the square root of x plus h plus the square root of x. And then we can do what? Cancel out the h. So what's left in the numerator? 1. Good. So we have 1 over the square root of x plus h plus the square root of x. Now we can direct substitute. So if we do that, what's that going to give us? Good, right? So 1 over square root of, it's going to be x plus 0 and square root of x, which is just 1 over the square root of x plus the square root of x. Those are actually like terms, right? So if we combine those, what's that going to give us in the denominator? What's the square root of x plus the square root of x? 2 square roots of x, right? So we get 1 over 2 square root of x. That is our derivative. So again, just don't forget all that stuff we learned back in chapter 1 with these limits, right? Because whenever you end up with those square roots, think about your conjugate, multiply top and bottom by that. And then once you simplify, then you should be able to direct substitute and find your limit that way. Any questions on that one? All right. Now we want to find f prime, find our first derivative, if f of x is equal to 1 minus x over 2 plus x. And that's just a period there at the end of that sentence, right? So just kind of ignore that. All right, so same formula we've been using, right? F prime is the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so if we do that this time, we've got to substitute the x plus h here, but we have multiple x's in that fraction that we have to plug into. Okay, so just be careful when you do this. It's going to be 1 minus x plus h over 2 plus x plus h minus, then we have our f of x, which is 1 minus x over 2 plus x, and all of that is over h. So that's just the substitution step. Because we have a rational function, that x plus h gets substituted in place of both of those x's, so that's what it should look like. Any questions on that step? Okay, now I'm going to go ahead and drop these parentheses and distribute here. So we'll have limit h approaches 0, distribute the minus. That's going to give us 1 minus x minus h over 2 plus x plus h. And we just have our 1 minus x over 2 plus x. All that's over h. Now, we have a fraction within a fraction. We can't direct substitute at this point, so we've got to simplify first. What do you think we could do to simplify this so that we could actually calculate this limit now? All right, so do we have a factor of h that we could factor out anywhere? All right, looks like I lost my video. Give me 1 second. I'm going to reload and I'll be right back. All right, there we go. Can everybody see that okay now? Good. All right. So what can we do at this point then if we want to simplify this? We don't have any common factors that we can bring out. Okay. Yeah, so we could actually get a common denominator with those two fractions up top and then combine those fractions, right? So that's going to be our best bet this time. What would our common denominator need to be then? Good, right? We need the 2 plus x plus h from the first fraction and the 2 plus x from the other fraction. That's going to be our common denominator. That means the first fraction we're going to have to multiply by what then? So if our common denominator is 2 plus x plus h times 2 plus x, what are we missing in that first fraction? What are we going to have to multiply by? The 2 plus x, right? I'm going to take everything in my numerator here, multiply that by 2 plus x, and then same thing with the denominator, take everything in the denominator, multiply it by 2 plus x. Okay? What are we going to have to multiply the other fraction by? Good, the 2 plus x plus h. So again, I'm going to take the 1 minus x here. I'm going to multiply it by 2 plus x plus h. And then down here, I've got the 2 plus x already. I'm going to multiply it by 2 plus x plus h. Don't forget, all of that stuff is still over h. Any questions about that step? Okay, now we do need to multiply out these numerators here so that we can actually see if we have any like terms to combine when we put these fractions together. Now, it's up to you. If you're good with distributive property and just want to distribute, it's probably easiest to do the 2 times everything and the x times everything, then come over here and do the 1 times everything and the negative x times everything. You can also use the box method, right, if anybody's familiar with that, where you actually take all of your terms. In this case, I've got 3 terms and 2 terms. So I would do like the 1, the negative x, and the negative h up here. I would do the 2 and the x here. And then I would just multiply everything together. So that would give us 2, negative 2x, negative 2h, x, negative x squared, negative xh. If you have any like terms, you want to combine those. So in this case, the negative 2x and the x would combine. And so that would give us 2 minus x minus 2h minus x squared minus xh. So now I know that this is the limit as h approaches 0. 2 minus x minus 2h minus x squared minus xh. Then I'm subtracting everything that I get over here, because remember, we have our common denominator, so we can actually put these together now. It's 2 plus x, 2 plus x plus h. And then I can do the same thing with these two. If you want to do the box. We have a 1 and a minus x. We have a 2, an x, and an h. It's going to give us 2x h, negative 2x, negative x squared, and negative xh. Again, combine your like terms. The x and the negative 2x should give us a negative x. So we have 2 minus x plus h minus x squared minus xh. And all of that's still over h, though. Any questions on that step? Just multiplying those out. Okay. Now, at that point, we can combine like terms. Okay, so if we do that, remember, we're just combining everything in that numerator now that we can. The limit, h approaches 0. What are we going to be left with in the numerator if we like terms? Yeah, just the negative 2h and the minus h, right? Because the 2 minus 2, that's going to cancel out. We have a negative x minus a negative x. That becomes a plus, so the x's cancel out. We have a negative x squared minus a negative x squared. Again, that becomes addition. Those cancel out. And the negative xh minus a negative xh, those also cancel out. So all that's left is the negative 2h minus an h, which is going to give us what if we combine those? What's negative 2h minus h? Negative 3h, right? So we're left with negative 3h over 2 plus x times 2 plus x plus h all over h. Okay. Now what can we do? Yeah, we can actually cancel out the h from the negative 3h and the h here. If you don't see exactly how that happens, remember when we divide, we can multiply by the reciprocal. So this is negative 3h over 2 plus x times 2 plus x plus h. And we're really just multiplying by 1 over h. And at that point, those h's would just cancel each other out. And so you can go ahead and just say, well, those cancel. And so we're left with the limit as h approaches 0. Now we have negative 3 over 2 plus x times 2 plus x plus h. So then our last step is to actually find the limit. Okay, so we can plug in. So what's that going to give us as our limit if we do that? Good, right? So we have negative 3 over, this is 2 plus x times 2 plus x plus 0 now. So that's just a 2 plus x times 2 plus x. You don't need to distribute them, but because they are the same factor now, we can actually just write this as negative 3 over 2 plus x squared. Okay. And so that would be our derivative for that one now. All right, so I know we are out of time. I'll hang out for a couple more minutes in case there's any questions about this one. I am going to push the homework back at least one day. Okay, so just know that it won't be due tomorrow night by midnight. But at least go ahead and get a start on it, right? Because you should be able to do a lot of these derivatives at this point based off the examples we've done. Let me know if you've got any questions. Send me those questions using the Ask My Teacher button and WebAssign. Again, if you have any questions about your test or any of the feedback that I provided, either send me an email or if you want to drop in during student hours, that's a great time to ask me those questions, okay? Otherwise, have a great afternoon, and I will see you all tomorrow.